Okay, so let's talk about electrolysis. Electrolysis is the non-spontaneous redox reaction. In other words, E cell will be less than 0. So if we force a redox to go one way instead of another in order to do something, then we have an electrolytic cell. So we have to attach a source of power, be that a battery or an electric grid, and make it go. So on the right here, we have an example of something you should probably not do at home, but you could. Well-ventilated space. Well-ventilated space. Anyway, you can actually do the electrolysis of water using graphite pencils and a 9-volt battery, which is interesting, but again, not a great idea. Anyway, Wikipedia, giving you things that are dangerous to do at home. You can add voltage to make the electrons go the other way. So there's a certain potential involved with every electrolytic cell. We know that. And we can figure out how to flip it so we know what it would be for galvanic. And then if you flip that, it would be negative of that for an electrolysis cell. And so you have to add at least that much voltage, probably a little bit more, in order to make it go back the other way. So what do we use this for? Big business, refinement of metal ores. All the way back as far as 1890, we've been getting aluminum from bauxite using electrolysis. We use it for electroplating. So when we put thin layers of metal on the outside of another metal, so actually electroplating can be used as a part of galvanizing. But you get the idea. You put a little layer on by using electrolysis. And finally, you can also use it to manufacture commodity chemicals. And commodity chemicals means things made on a global scale. So think very large factories. That's usually how we get our sodium and our chlorine solids. Okay. So for our mathematical relationships, we have a couple new ones. Q equals IT and Q equals NF. Q is the amount of charge measured in coulombs. I is amps, it's current. You may remember if you took physics at one point doing current and voltage calculations in order to find watts. We're not doing that. We're just doing Q equals IT. And T here is time, lowercase t is time. Current is also equal to the moles of electrons times Faraday's constant. So what can we do with this? We can determine how much mass will be deposited on something, how much current you'll need to supply to perform an electrolytic task, and how long it might take to perform an electrolytic task, all by using these relationships. So let's try the thing. How much gold 3 plus will be deposited on nickel spoon if 5.00 amps were applied for 6 minutes? So whenever you see one of these questions, the first thing you have to figure out is how many moles of electrons we have going back and forth in our balanced chemical redox equation. So if we wrote our balanced redox equation for this, we have nickel solid going to nickel 2 plus, and we've got gold 3 plus going to gold solid. And remember, this is pushing it the wrong way, so we should get a negative E cell. And you do, by the way. All right, so from here, we can start doing our calculation. We're going to use our Q equals IT to establish how much charge is transferred. So 5 amps is the same as coulombs per second, so 5 coulombs per second times 6 minutes. Oh, we got to do a unit conversion because we have to go from minutes to seconds to use it with amps. So 6 minutes times 60 seconds per minute gives you 1.80 times 10 to the third coulombs. Now we're going to use the Q equals NF. So N times 96,485 is equal to that 1.8 times 10 to the third coulombs. And if we solve for N, we get 1.87 times 10 to the negative 2 moles of electrons transferred. Okay, so if we go back to that balanced equation, we realize that we're moving 6 electrons each time we do the thing. So you're going to take the number of moles of electrons, multiply it by 2 moles of gold from this balanced equation, divided by the 6 moles of electrons we're transferring, times 197 grams per mole for gold, and you'll get 1.23 grams deposited on the spoon. Okay, so in total, you have to have a balanced redox equation so you know how many moles of things you've got to electrons that are moving. You use the Q equals IT, the Q equals NF, and then you solve for mass. We'll calculate for time in this example. How long would you need to run a 15 amp current, which is actually very high, by the way, through a cell of molten iron 3 chloride to produce 1 kilogram of iron? So this is actually a thing that people do. Iron 3 chloride is a mineral that we extract iron from, and our reaction then will be iron 3 chloride going to iron solid and chlorine gas. This is not currently balanced. So we split it into the half reactions, and I used the oxidative state of the iron, even though it's iron chloride, in order to not have to worry about crazy balancing of mass. Now that being said, in order to put these two things back together, we're going to have to cross multiply that 2 and that 3. So we get a relationship, and I'm just going to give the stoichiometry here. I'm not going to give the entire balanced equation. We have 2 iron for every 6 chlorine for every 6 electrons. And we're making 3 chlorine gas. Okay. So now that we have a nice balanced chemical equation, or rather, we have our stoichiometry, we're going to go ahead and use our Q equations to solve for time. We're going to start with Q equals NF because we have moles of electrons in a ratio with iron, and we need that because we want to make 1 kilogram of iron. So we calculate how many moles are in that kilogram, and then we're going to convert from iron moles to moles of electrons, and that is the N that we will put into Q equals NF. So here we go. 1,000 kilograms converted to grams divided by the molar mass of iron times the 6 electrons over 2 moles of iron. All of the rest of the stuff except for moles of electrons cancels. We multiply that times Faraday's constants, and we get 5.129 times 10 to the 6th. All right, now at this point, we're going to plug that into Q equals IT. Our I here is 15 amps. We're going to solve for time. When we do that, we get 3.42 times 10 to the 5th seconds, which is also 5.7 times 10 to the 3rd minutes, or 95 hours. This is a process that takes a decent amount of time and a lot of energy. But you get iron, which is a thing we use a lot in our modern world. Finally, we can do an electrolysis calculation for current, our I. What current is required to produce 1 liter of hydrogen gas measured at STP from electrolysis of water for 30 minutes? This is the reaction shown in our electrolysis example at the very beginning, except I hope that you would not use graphite as your electrode, and actually just don't do it at home. Anyway, water splits into hydrogen and oxygen gas. We know that we move 4 electrons in order to do this, because our oxidative state for hydrogen is +1. There are 4 of them, which means we have to move 4 electrons to make it work. Oxygen is -2, but it goes to 0, which means we moved 4 electrons to make it work. We start with Q equals NF again, because we need to know the number of moles of hydrogen gas that we're making. From there, we can get to moles of electrons needed. So how many moles of hydrogen gas is that? We're going to use the ideal gas law. Yeah, it's been a while. So PV equals nRT. And here we have STP, so standard temperature and pressure is 1 atmosphere and 0 degrees Celsius, because we have atmospheres we're going to use 0.08201, or sorry, 0.0821 for our R. 273 is our temperature, and the rest of it came from our problem. When we solve, we get 0.0446 moles of hydrogen gas. We know that for every 2 moles of hydrogen gas we produce, we moved 4 electrons. So we're going to use our stoichiometry. Easy as that. We now know the number of moles of electrons that we moved along in order to make that amount of hydrogen gas. We're going to plug that into the Q equals NF. And we get 8.61 times 10 to the third coulombs. When we plug that into Q equals IT, we need to make sure that our 30 minutes is converted to seconds because our current is going to be in amperes, which is the coulomb per second. When we do that, we get 4.78 amperes of current are necessary in order to produce 1 liter of hydrogen gas from electrolysis of water running for 30 minutes at STP. So generally speaking, you're going to use one Q equation, and then once you have Q, you'll use it with the other Q equation to get to your answer. To summarize, electrolytic cells are non-spontaneous. Electrical work is done in order to make it go the opposite way. They're used for a variety of applications, including electroplating and mineral extraction. Time, when you use Q equals IT, must always be in seconds. Otherwise, you won't get amperes out. Q equals NF often uses moles of material used or generated, so you need to balance your redox chemical equation before doing the stoichiometry involved to go from moles of stuff you made or used back to moles of electrons. And N is always moles of electrons for electrochemistry, which is something that I think we know at this point, but I'm going to remind you.